All right, let's get started. So we have been discussing about the AC analysis of a MOSFET, and by AC analysis, what we generally mean is that we want to find out the gain of the MOSFETs. So we want to discuss a little bit more about different MOSFET configurations today, which will provide different amount of gain based on the configuration. But before going there, I would like to quickly discuss about the homework 4 solutions, because homework 4 is very important for your exam, which is due this Wednesday, so day after tomorrow. So again, a little bit about the exam. All the details have been posted on Canvas. Please go through them. It will be very similar to your exam number 1 in terms of how the exam will be conducted. So please go over the details if you haven't done that already. Okay, so for our homework number 4, what we wanted to find out was the DC biasing point of the MOSFETs for various configurations. So for example, the first problem that dealt with a MOSFET, an N-channel MOSFET, which had a resistance connected at the drain and also a resistance connected at the source. So you were given this information that the threshold voltage of the MOSFET is 1.3 volt, K is equal to 32 milliampere per volt squared. So keep in mind that K is equal to your K prime times W over L. And again, K prime is equal to mu N times COX. So that's the mobility of the N-channel MOSFET times COX. And then this whole thing is K prime, that multiplied with W over L, that gives you the value of your K. Okay. Lambda you can assume to be 0 at this point. So that means that there is no channel length modulation. So your equation for saturation will be as simple as current, the drain current equal to K over 2 times V over drive squared. Okay, so ID equal to K over 2 times V over drive squared. That would be your equation when in saturation. Now, the first question asks with, to choose values of RS and RD so that the drain current is 4 milliampere as well as the drain voltage is equal to 2.4 volts. Now, finding out the value of RD is very easy because you are already given VDD, which is equal to 10 volts. You're already given the value of VD, which is the drain voltage that would be equal to 2.4 volts. And you're also given the value of the drain current, ID. So you know the voltage at the top terminal as well as the bottom terminal of this resistance. So both the top terminal voltage and the bottom terminal voltage of this resistance is known. Also the current through that resistance is known. Now we can just apply Ohm's law, right? Resistance equal to voltage divided by current, and that would give you 1.9 kilo ohm as the value of RD. To find out the value of RS, it's a little bit more involved. So there, what you can do is that you can assume that the NMOS is in active region. Why we are doing so? We'll show this later, that the NMOS is indeed in the active region. But first, you can start with an assumption that, okay, let us assume that the NMOS is in active region, and later we'll verify that. So if you assume that the NMOS is in active region, your equation will be this, RD equal to K over 2 times V over drive squared. And from there, you can find out what is your V over drive, because you already know the value of ID, you already know the value of K. That is already provided in the question, the value of ID as well as the value of K. So since you know both those values, you can find out what would be your overdrive voltage, and that will be equal to 0.5 volts. Now, you can write your V overdrive as VGS minus VT, that's by definition, and VGS is equal to VG minus VS, correct? So VAB is VA minus VB. That's again the definition of voltage. So you can find out what would be your VS, that would be VG minus VT minus V overdrive. And then since you know all the values of the gate voltage, which is grounded in this case, you know the value of VT and you know the value of V overdrive, you can find out VS to be equal to minus 1.8 volts. Now, since you have value of VS, you also know the value at the bottom terminal of the RS resistance, and you know the current through the RS resistance, which will be equal to the current through the ID resistance or the current through the MOSFET. Because again, because of KCL, the current has nowhere else to go. The amount of current that is flowing through RD will be the same amount of current flowing through the MOSFET, will be the same amount of current flowing through RS. So with that, you can find out what would be your RS. That would be the voltages at the 2 points of this resistance, the top terminal and the bottom terminal, the voltage difference between those 2 points or those 2 terminals divided by the current through the resistance. And with that, you can find out your RS to be equal to around 2 kilo ohms. Now you can check whether you are in the active region indeed. because now you have the values of all the components fixed. You also have the values, you also know the values of all the terminals, the drain terminal, the gate terminal, the source terminal of the MOSFET, and so on. So because you have information about all the terminals, what you can now do is that you can check or you can verify if indeed the MOSFET is in the active region. And for that, the equation is VDS has to be more than or equal to VGS minus VT. That's the equation of saturation, right? So if VDS is greater than VGS minus VT, the MOSFET will be in saturation. You already know the value of VGS minus VT, which is your V over drive is equal to 0.5 volt. And you know your value of VD as well as VS, which are 2.4 volts and minus 1.8 volt respectively. So you know what is the value of VDS, that is 4.2 volts. And definitely that is more than 0.5 volts. So your VDS is more than VGS minus VT, which means that the transistor is in your active region. All right. The second part of the question says that assuming the current stays same to be equal to 4 milliampere, you need to find out the largest value of RD for which the FET or the transistor stays in the active region. So what is happening is that you can assume that the value of this RD is increasing. If the value of RD increases, the voltage drop across RD also increases. Since the total voltage drop from VDD to VSS is fixed, if one of the voltage drop increases, the other voltage drops will eventually reduce. Now, since the current is fixed, the voltage drop across RS is also fixed, which means that if the value of RD is increasing, the voltage drop across the MOSFET, so the VDS of the MOSFET has to reduce because this drop is increasing, this drop stays constant, so the drop across the MOSFET has to reduce. Right? The total voltage drop from VDD to VSS has to be 10 volt minus 10 volt, so the total voltage drop has to be equal to 20 volts, right? KVL. Now, then that's why you are asked to find out the largest value of RD for which the FET still stays in the active region, because as the value of RD is increasing, VDS across the MOSFET will keep on reducing, and at some point you'll see that you'll not satisfy this condition anymore. VDS had to be more than equal to VGS minus VT for the transistor to be in saturation. Because VDS is now reducing, at some point this condition will not be satisfied because VGS is constant, VT is also constant, and VDS is reducing. So the minimum value of VD, or actually you can start from the point that your VDS has to be greater than equal to V over drive. So the minimum value of VD for which this condition is satisfied, that minimum value of VD is called VD sat, and that VD sat will be V over drive plus VS, because the minimum value of VDS is V over drive, right? Remember this curve of VDS versus ID, and when your VDS is more than, let's say this point is V over drive, when your VDS is more than V over drive, the transistor is in saturation. So the minimum value of VDS at which the transistor is in saturation is equal to V over drive, given by this equation. So the minimum value of VD, that would be V over drive plus VS, because VDS equal to VD minus VS. And you now know the value of V over drive, you know the value of VS, you can find out what would be the minimum VD. And if you know what would be the minimum VD, you can find out what would be the maximum RD, because you know the voltage value at this point, you are finding out the voltage value at this point, you know the current through the resistance, so you can definitely find out what is the value of the resistance. Question?
How did you know VS is constant?
From here, right? Yeah. So you are assuming that the current is still constant. Current is 4 milliampere. So if the current is 4 milliampere through this, RS is not changing, right? The current through RS is constant. The resistance of RS is constant. So the voltage across RS is constant. So that means VS has to stay constant. But good question. Okay, the second question was diode connected MOSFET, and we already discussed about this a little bit. We'll discuss this in detail when we look into more AC analysis related problems. But for a diode connected MOSFET, your VD is equal to VG, correct? The drain voltage is equal to the gate voltage. Drain and gate are connected together. So your VDS will always be greater than VGS minus VT, because VDS will be equal to VGS and VT is a positive quantity for the N-channel MOSFET. So VDS will always be greater than VGS minus VT, which means that this device will always be in the active region or in the saturation region. And again, you are asked to find out what is the value of RS needed to get ID equal to 1.25 milliamperes. You can use the same formula for the device in active region, that V overdrive equal to square root of twice ID over K, and you know the value of ID, you know the value of K, you can find out what would be your V overdrive. And if you know what is the value of your V overdrive, you can find out what is VGS, because VGS minus VT, that is equal to your V overdrive. So your VGS will be V overdrive plus VT, and from there, you can find out what would be your VS, what is the voltage at this terminal. That is VG minus V overdrive minus VT, and that gives you 5.8 volts. Now, if you know the value of VS, you can find out what would be the value of RS. That would just be VS divided by ID. And remember, ID, that is the current at the drain of the transistor, will be equal to the current at the source of the transistor because of KCL once again. All right. The second part of the question asks that if RS is equal to 6 kilo ohms, so instead of RS being this 4.64 kilo ohms, if RS is equal to 6 kilo ohm, you need to find out what would be ID and what would be your VS. So in this case, you can write down VS to be equal to 6 kilo ohm, that is RS times ID. Correct? So that's just from Ohm's law, that the voltage VS will be equal to the resistance RS multiplied with the current that is flowing through it. You can also write down ID as K over 2 VGS minus VT whole square. That's from the equation of the MOSFET. So we have one equation from Ohm's law and the other equation from the property of the MOSFET, that ID equal to half K times VGS minus VT whole square. Now, you know the value at the gate terminal, which is 7 volts, because gate and drain are connected together. The value at the source terminal will be 6K times ID. So 6 kilo ohms times ID, that's the value at the source terminal. So you know what is the value of VGS, that will be 7 minus 6000 ID. And VT is equal to 0.95 volts. So you can also put that over there. And now you have an equation, a second order equation of ID, where all the other values are known. K is known, all these voltages are known. What is unknown is just this ID. So you can numerically solve this ID, or you can put it using or find it out using a calculator, that ID to be equal to, it could be two different values, 0.972 milliamperes or 1.05 milliamperes, because you know, whenever you solve a quadratic equation, there could be two possible roots, right, in a quadratic equation. Now, out of these two, you'll see that one of them will satisfy the active condition for the MOSFET. So this equation will be true for one of those values, and for the other value, the equation will not be true. In fact, in this case, what will happen is that if your ID is equal to 1.05 milliampere, your VS will be 6000 times 1.05 milliampere, so that will be 6.28 volts. But your V overdrive will be VGS minus VT, so gate voltage is 7, source voltage is 6.28, and VT is 0.95. So overdrive will be a negative voltage. In other words, your gate to source voltage will be less than your threshold voltage. If the gate to source voltage is less than the threshold voltage, the NMOS will be off. So the condition of operation for any kind of NMOS or PMOS based circuit in this course will be that the transistor has to be on, which means that the gate to source voltage has to be greater than threshold voltage. And the second condition is that it needs to be in saturation. So in this case, this equation needs to be satisfied. So you're already assuming that this equation is true, but if you take ID to be equal to 1.05 milliampere, you'll see that the NMOS will be off in this case, because VGS will be less than VT. But on the other hand, if you take ID to be 0.972 milliampere, you can again find out what would be your VS, because you know the value of this resistance, you know the value of the current flowing through it, so you can find out what would be the voltage at the source. So as you find out the voltage at the source, you can find out what is VGS. And in this case, you'll see VGS is this 7 volt minus 5.83 volts. So that is more than your 0.95. That's the threshold voltage of the MOSFET, which means that the NMOS is on. So the NMOS is in on and it is in the active region. So you'll take this to be your solution of current ID. So you can find out what is your ID, that will be equal to 0.972 milliampere, and VS will be 5.83 volts in this case. The third question, again, it's a very similar to question number 1, but the difference is that at the gate side, you have a division of voltages using the RG1 and RG2 resistances. But except for that, you again have the RD resistance, you again have the RS resistance, you're given the value of VT, value of K and lambda, and you need to choose RG1 and RG2 so that your gate voltage is 4.5 volts and RG1 in parallel with RG2 is 75 kilo ohms. So you can find out what is the gate voltage first. So the gate voltage will be a voltage division of between RG2 and RG1. So you get VG, the gate voltage at this point, to be equal to RG2 divided by RG1 plus RG2. That's again just from the voltage division theory that we learned in the first 3 or 4 lectures in this course. And you also know that the total value of resistance is RG1 plus RG2. So that's a series of RG1 and RG2. And you also have the value of VG. You know the value of RG1 in parallel with RG. From there, you can solve for RG1 and RG2, and you can get RG1 to be equal to 200 kilo ohms and RG2 to be equal to 120 kilo ohms. You can choose RS and RD so that ID equal to 4 milliampere and VD equal to 6 volts. So that will be exactly similar solution to problem number 1. The method will be very similar. The values could be different. So I'm not going over that part again. The third question, part C, was to calculate GM. That's the transconductance of the device. And you know GM will be equal to K times VOV. Now, while you were finding out the value of RD and RS, you found out what should be VOV from this equation, that VOV equal to square root of twice ID divided by K. And from there, you can find out your VOV. You already know your K. You can find out what is your GM as a multiplication of those two. You can use other formulas of GM. GM, you know that GM is equal to twice ID, square root of twice ID times K. And it is also equal to twice ID divided by VOV. So whatever equation you use, eventually you'll see that your GM value will be same, because all these equations do talk about the same thing eventually. And all of those equations are derived from the same equation, which was this equation of your current in the active region, which is ID equal to K over 2 times V over Z squared. You can also find out what is RO if the value of lambda is given. If the value of lambda is equal to 0.01 per volt, you can find out RO to be equal to 1 upon lambda ID, as it was proved in class, and then you can find out what would be the output resistance. In this case, it comes out to be about 25 kilo ohms. There are a few exercise problems as well, which we did not need to submit as part of your homework number 4, but please go over them because that will give you a better idea of how to solve any kind of DC analysis for a MOSFET. So just go over the exercise problems 4, 5, and 6 before the exam so that you have a good idea about how to do the DC analysis of these different kind of circuits. Okay, any questions here? All right, if not, let's go back to our AC analysis that we have been doing in the last few lectures. And yeah, so this is where we were at during the last lecture, that for this circuit, which is again very similar to your homework number 4, problem number 3, in terms of the DC analysis, that you have this RG1 and RG2 resistances, you have RD as well as RS, and you are applying a AC voltage through this AC coupling resistance over here. And we already solved this circuit. We found out what should be the effective GM. The capital GM is basically the effective GM of the entire circuit, whereas the lowercase GM is the transconductance of the NMOS device. So for example, in this case, the capital GM tells you that what is the current that you expect, what is the current that you expect in this branch as you are changing the input voltage over here. Okay. But on the other hand, the small GM says, what is the change in the output current, that is the output current going through the MOSFET as well as the drain and source, as you are changing the VG voltage over here, or the gate to source voltage of this MOSFET. So that's what the small GM or the lowercase GM tells you. that what is the transconductance of this device? That's your lowercase gm. The uppercase gm is the transconductance of the entire system, where you have multiple resistances, capacitances, and all other things. And this is what we proved in the previous lecture, that the uppercase gm in this case will be lowercase gm divided by 1 plus lowercase gm times RS1, because in this case, the gm as well as the gain of the system will be degenerated by this source degeneration resistance RS1. So your transconductance eventually reduces. And we found out that the value of the voltage gain eventually turned out to be about minus 1.14. So even if you, the output voltage is just 1.14 times the value of the input voltage. So you have a very, very small amount of gain. On the other hand, in the previous case, what you had is this same bypass resistance, but if you also put a bypass capacitance. So let's analyze the same circuit with a bypass capacitance. What that will mean is that you'll not get the degeneration in the GM, you'll not get the degeneration in the gain. So if the RS1, if the source resistance is bypassed with another capacitance, which means that for your AC analysis, you can assume that capacitance to be a short, which means that there will be no degeneration resistance in the effective scenario. So in that case, your capital GM will be small gm divided by 1 plus gm RS with the source degeneration. But because you are bypassing the source degeneration with this additional capacitance, your RS will be almost equal to 0, right? Or RS will be equal to 0. The effective RS that you'll see as a parallel combination of the short and the original RS1. So your capital GM will now be equal to your small gm, which we expect, because what you're doing is that you're saying that I'll not have the source degeneration resistance anymore, I'll just short it out. Which means that you'll go back to your original GM, and that's why your uppercase GM, that's the original, that's the overall GM of the system, will be equal to the GM of the NMOS, GM of the device. And you already have found out what would be the GM of the device in the previous problem. So just go back to the previous one if you don't remember the values. So your GM was given to be 8 milliampere per volt. So your capital GM will be equal to 8 milliampere per volt. Your voltage gain in this part of the system, let's say you just ignore the input side for a moment, and let's say you want to find out the voltage gain in this part of the system, that would be equal to minus GM times, or this capital GM times R equivalent at the output. You already know what is the R equivalent at the output side. That is equal to, over here. So the R equivalent at the output, what you see is the RD resistance connected to AC ground, connected to VDD. You also see a RL resistance connected to ground. So it will be a parallel combination of those two. And of course, if you consider the RO of the MOSFET, it will be a parallel resistance of RO that will come into picture. But in this case, we are just ignoring it for now. That RO, we are just assuming RO is very high. So your RL equivalent, the load resistance, equivalent load resistance at the output will be just a parallel combination of RD and RL. And that will be equal to 4 kilo ohms. So if you put those values, you'll see your voltage gain will be equal to 32 for this part of the circuit. And of course, you'll see a voltage division at the input side. So this is very similar to your first few lectures in this course, where you discussed that, okay, if there is an input resistance at the op-amp, and if there is a source resistance at the voltage source, you'll see a voltage division at the input side. So that voltage division at the input side is in between this RS resistance, which is 40 kilo ohms, and this input resistance at the gate, which is RG1 in parallel with RG2, that was equal to 240 kilo ohms. So you'll see a voltage division, which is input resistance divided by input resistance plus RS. So 240 divided by 240 plus 40. So this is the 240 kilo ohms, and that's the 40 kilo ohm source resistance. So 240 divided by 280, that's the factor you'll have at the input side because of the input side voltage division. That multiplied with GM times R equivalent, which was 32 or minus 32, that gives you the final gain of minus 27.4. Now you see that just with this bypass capacitance, you were able to increase your gain to minus 27.4. In the previous page, the gain was just minus 1.14. So from a gain of 1.14, you are able to increase the gain to 27.4. And you basically get both best of both worlds because you have this RS resistance that gives you the flexibility in terms of the DC biasing, but you don't suffer from the loss or from the degeneration in the AC gain. So that's the advantage of having this bypass capacitor along with this degeneration resistance. So this was just a SPICE example of the same thing. You can just go for what happens in the SPICE example and look at, if you have time, just run a SPICE simulation and check whether all these values match up and so on. So it's just the same circuit, but we are just simulating it in SPICE to make sure that what we calculated is very similar to what you'll see in the SPICE simulation. All right, so I think we can move to the next part of the lecture. Here, what we are going to show today are different configurations of MOSFETs. Some of them you already have seen, but we are trying to take a systematic approach of discussing different configurations of MOSFETs and their gains in terms of the AC analysis that you want to do. So first of all, we want to discuss something called a common source amplifier. We also have common gate and we also have common drain. So these are the three configurations that you'll find for any kind of MOSFET based circuits, because remember that you have, this is how your MOSFET looks like. You have the gate terminal here, you have a drain terminal over here, and you have a source terminal over here. Now, what you can do is that you can apply your input to one of these terminals, and you can look at the output at some other terminal, which will leave one terminal out of these three. So one terminal will be input, the other one will be output, and the third terminal will be called a reference terminal or a common terminal, because your input will be applied between the one of the terminals and the common terminal. So let's just think of it as a ground in your any kind of electrical circuit, that you measured any kind of voltage at a particular terminal with respect to the reference terminal or the common terminal, right? Here also it's the same thing, that you apply your input between the input terminal and the common terminal or the reference terminal, and you look at your output between your output terminal and the reference terminal. So because there are three terminals, you can have one of them as input, one of them as output, and one of them as your reference terminal. So there are a few possibilities. Of course, you can create many different possibilities with this, but three possibilities which are interesting and which we'll take a look at is, first, you can apply your input at the gate. You can look at the output at the drain terminal, while your common terminal or the reference terminal will be the source. And that would be called the common source configuration. That your source terminal is the common terminal, your input is applied at the gate, and your output is observed at the drain terminal. Okay, so that is the definition of your common source configuration. And this is something we have already looked at in the previous handout, which was already shared on your campus, that you were applying your input at the gate terminal, you are looking at your output at the drain terminal, and let's say this source terminal, instead of having the source rejection resistance, let's say this is just connected to ground for now. You can connect the source rejection resistance, but that will not change the configuration, that your input is still at the gate and output is still at the drain. And why we are calling this as the common terminal, because your gate to source voltage is that, right? Still your ID or the current is dependent on the gate to source voltage, and that source will be the common terminal even with the degeneration resistance. Although it will not be connected to ground directly, but you can still regard it as the common terminal in that case. But if you just disregard the degeneration resistance for a moment, it's very easy to understand why this is called a common source, because your input is at the gate, your output is at the drain, and the common terminal or the source terminal is grounded. Okay, you're looking at your input between the gate and the common terminal, and your output is between the drain and the common terminal. Okay, so that would be called your common source. We'll look at the common source with the source regeneration again, but we have already done this AC analysis in the last lecture. We'll just repeat it so that it gets imprinted in your mind that, okay, this is how we need to do the AC analysis for any kind of configuration. So we'll just repeat that. But before that, I want to talk about the other configurations a little bit more. What you can also do is that you can apply your input at the gate. You can look at your output at the source terminal. And in that case, your common or reference terminal will be the drain terminal. So input at gate, output at source, and the reference terminal will be the drain. That is called the common drain configuration. We'll also look at the common drain configuration in today's lecture, because in your homework 5, you'll see that there is a two-stage amplifier in your homework 5. Maybe I can just open it. All right. So in your homework 5, as you see that there is a two-stage amplifier. Why are we calling it a two-stage amplifier? That's because so you already know about this to be the resistance associated with the source. You're coupling that input value with help of a capacitance. You have this RD1 and RD2, which establishes the DC bias at the gate of the first stage MOSFET. You have RD1, you have RS1, and you have this bypass capacitance. So up to this point, it's pretty well known to you at this point, right? So you can solve the voltages and currents at any point, given the information you have from the previous lectures and also from this class. What you don't know yet is what would be the behavior of this part of the circuit, or specifically this MOSFET and this resistance configuration. But what you see here is that the input is provided at the gate, right? The output is taken from the source of the MOSFET. Remember that this is the source terminal. The current direction is always provided on the source terminal. And the drain terminal is connected to the AC ground, which is your VDD. So in this case, your input is at the gate, output is at the source, whereas the drain terminal is the common terminal or the reference terminal. So this is called a common drain configuration. So common drain configuration, and you'll also see that it will be called a source follower configuration. So common drain or source follower, that actually says the same thing. And why is it called a source follower? We'll prove this today, that the gain of this system, gain of this circuit will be equal to 1. So whatever you provide at the gate, you'll get the same value of the AC signal. So let's say you have an AC signal which is 10 millivolt in amplitude. You'll get back an AC signal which is again 10 millivolt in amplitude at the output, which is at the source terminal. So that's why it's called a follower, that it follows whatever input you have applied, and that followed voltage is available at the source. That's why it's called a source follower, that your output is at the source and it's a follower of your input. The output is just follows your input with the exact same amplitude. So in other words, your gain will be equal to 1, and that's something we'll prove for this common drain or the source follower configuration. Question? What would be the purpose of having? Great question. So if the gain is equal to 1, what's the purpose of having it anyway? So because it's not being used as an amplifier. Why this is usually used is to drive a certain amount of load. So for example, let's say this resistance is very small. So let's just think about a spectrum analyzer or an oscilloscope which is in 50 ohm. So you know that the input impedance of the oscilloscope needs to be very high, so that you are able to see the voltage that you want to see from the circuit. But if the oscilloscope is configured in a 50 ohm mode, or if you want to see the signal in a spectrum analyzer or any other instrument which is for which the input impedance is 50 ohms, you will see that it's very hard to drive that instrument from a single stage amplifier. And that is because the single stage amplifier, this amplifier is designed to provide some amount of gain, assuming that you have a very high load impedance. If your load impedance is very small, that load impedance will come in parallel with this RD, correct? So that's what we discussed earlier. Let's just go back a little bit. All right. So for example, this linear equivalent circuit of a MOSFET, that you have the RO of the transistor, but you have your RL, whatever load resistance you're connecting, in parallel with this RO of the transistor. So if this RL is very small, let's just say it is 10 ohms. It does not matter if your RO is 100 kilo ohms. The parallel combination of 100 kilo ohm and 10 ohm will be a very small resistance, which is 10 ohms. Now, what would be the gain of the entire system? That will be GM multiplied with the equivalent resistance that you see at the output, which will be a parallel combination of this RO and RL. So GM multiplied with 10 ohms, that would become your gain. So if your load is very small, you cannot expect that gain in your common source configuration. So we have already looked into the common source configuration, and in common source configuration, we saw that your gain is minus GM times RT, or when you have the source degeneration, it almost becomes minus of RD divided by RS. Still, you get some positive amount of gain. But as soon as you connect a load resistance, as soon as you connect a very small load resistance like this over here, in this case, what was the value of RL given? Let me check. So for now, it's fine. So RL was not given to it. Yeah, so for example, here, RL was given to be 220 ohms. So that was a very specifically, it's a very small value of resistance as compared to the other resistances, which are, let's say, mega ohm or in kilo ohm range. So what would happen is that if you don't put this second stage as a driver, the gain of your first stage will be very, very low. Because the gain of your first stage will become this minus GM times RT in parallel with RL. And because RL is very small, your GM times RT will suffer, or GM times RT in parallel with RL will suffer. So that's why what you want to do is that you want to put a second stage as a driver. You know, will show that the gain of this stage will be equal to 1. But even if this RL is very small, the gain will still remain 1. And that's what you want, that you want very high gain out of this stage, and then the second stage will just work as a buffer. It will try to drive any amount of load that you put at the output side, but with a gain of equal to 1. So that's the purpose of this second stage. And the buffer or driver is something that you'll see again and again in this course, and also if you take any other advanced course in circuit design. All right. So coming back to our AC analysis, that okay, this is the second configuration, that your gain is your input is at the gate, your output is at the source, and your common terminal of that is at the drain. There is one other interesting possibility where you apply your input at the source, you look at your output at the drain, and your common terminal is at the gate. So that is called a common gate configuration. So we'll also look at the common gate configuration as well. But for now, let's start with the common source, and we'll also look at the common drain, because that will be helpful in solving your homework number 5. Okay, so now for common source, again, we are looking at a more advanced version of common source where you have the source degeneration resistance. So what you do here is that you just draw the linear equivalent model or the AC small signal model of the MOSFET. So this is the AC small signal model of the MOSFET, that you are applying an input voltage at your gate. So your VG is equal to your V input. You develop a VGS across the gate terminal and the source terminal of the MOSFET. So this is the source terminal of the MOSFET. And at the source terminal, you have a resistance RS1 connected to the ground. The current source with which you represent the MOSFET, that is GM times VGS. So GM times the gate to source voltage, the gate to source AC voltage will give you the AC current flowing through the MOSFET. So that's what your small signal equivalent model looks like. Of course, in this case, you can find out your VGS to be equal to VG minus VS, and you already know the value of the current that is flowing through the source terminal and eventually flowing through the RS resistance. That value of current is GM times VGS, because this is the current that is flowing through. All of that current has to flow through the RS1 resistance. There is no other path for the current to go. So all the resistance has to flow through the RS1 resistance, which means the value of voltage at the source terminal will be GM times VGS, that's the current, times RS1, that's the resistance. So your VS will be GM times VGS times RS1. And VGS can be written as VG minus VS, that will be equal to VG minus GM times VGS times RS1. So you can write VGS times 1 plus GM RS1 equal to VG. Or you can write VGS to be equal to VG divided by 1 plus GM RS1. Again, you see that this is the degeneration factor, 1 plus GM RS1. So your ID, that's the drain current, will be GM times VGS. That will be equal to GM divided by 1 plus GM RS1 times VG. So in terms of the whole system, as you are applying this input voltage over here, that is equal to Vi. So remember Vg is equal to Vi because the gate voltage is this point's voltage, which is same as the voltage that you are applying over here. So this is equal to capital Gm times the input voltage that you apply. Just from the definition that this uppercase Gm is the transconductance of the entire system, and the lowercase Gm is the transconductance of just the MOSFET device. So capital Gm is ID divided by Vg, that is equal to Gm divided by 1 plus GMRS1. And of course, your capital Gm will be less than equal to your lowercase Gm, depending on the value of RS1. Of course, if RS1 is equal to 0, then your capital Gm will be equal to your small gm. And that's the scenario when you have the bypass capacitance along with the source rejection resistance. So if you put the bypass capacitance over here, then your RS1 effectively will become 0 at high frequencies, and in that case, capital Gm will be equal to small gm. All right, so you can write your gain to be equal to the capital Gm times the output resistance that you see for the entire system. And again, you can intuitively say that that is correct, because what is the definition of capital Gm? That's the transconductance of the entire system. Transconductance of the entire system is basically current output of the entire system divided by, let me write it in a different place because there's not much space over here. So I'll write it over here, that capital Gm is equal to AC current output of the entire system divided by AC voltage input of the entire system. Okay. Now capital Gm times R out of the entire system, that will be equal to I out of the entire system times R out divided by you have V in. So you already have the V in the previous equation. So capital Gm times R out is I out times R out divided by V in. What is I out times R out? Output current multiplied with output resistance. That is output voltage, right? From Ohm's law. Voltage equal to current multiplied with resistance. So that will become your V out over V in. And that's the simple proof that, okay, your gain is equal to capital Gm times capital R out, where capital Gm is the transconductance of your entire system, R out is the output resistance of your entire system. So now you already have found out what would be your transconductance of the entire system, that is minus Gm divided by 1 plus GMRS1. And what is your, or basically Gm divided by 1 plus GMRS1. And what is your R out? R out is the equivalent resistance that you see at the output side. What is that equivalent resistance? That is RT. We do not write it here, but yeah, I think we are writing this here. That RL equivalent is equal to RD, that is the resistance that you see looking in this direction, in parallel with whatever resistance you see in this direction. Right? So you see some resistance looking into this direction, and you also see some resistance looking into this direction from the output side. And the parallel combination of those two resistances will be equal to your equivalent resistance at the output. Right? That's same as whenever you try to find out equivalent resistance at any terminal. What do you find out? That from that terminal, you try to find out the resistance looking into ground in all possible directions and take the parallel combination of that. So let's just say you have a network that looks like this. And you are asked to find out the resistance at this point. Let's say this is your R out. So what would be that resistance? The resistance will be the resistance looking into this direction in parallel with the resistance looking into this direction. Okay. And in that case, you'll see that if this is R1, this is R2, and this is R3, it will be a parallel combination of R1, R2, and R3. So that's the same thing we are saying over here, that the resistance at the drain terminal will be the resistance looking into this side, top side, looking up, you'll see RD, and looking down, you'll see the effective resistance of the MOSFET and this RS resistance. We'll try to find out what would be that effective resistance. But for now, let's just represent that effective resistance as resistance looking into the drain of the MOSFET. That in parallel with RD will be your equivalent resistance. Okay, now from this particular equation, if your RS1, if your resistance is much less than 1 upon GM, or GM times RS1, if that is much less than 1, then this voltage term reduces to minus GM times R equivalent, because GM times RS1, that is much less than 1, so you can just ignore it in this scenario, in this condition, that if your RS1 is much lower than 1 upon GM. On the other hand, if your GM times RS1 is much higher than 1, if your GM times RS1 is much higher than 1, then you can write this equation that is shown on top as the one that is shown on bottom. And what you're doing here is that you're just dividing the numerator and denominator with GM RS1. So you'll get minus of 1 upon RS1 in the numerator, and you'll get 1 plus 1 upon GM RS1 in the denominator, times RL equivalent. Now, of course, if GM times RS1 is much higher than 1, this term will be much higher than, or this term can be neglected. 1 upon GM RS1, that would be much lower than 1, then it can be neglected. So this term goes away in this scenario when GM times RS1 is much higher than 1. And then this equation reduces to minus of RL equivalent divided by RS1. And this is what we had been talking about all the time, that if your RL equivalent, if the equivalent resistance looking at the drain is equal to RD, then this equation just becomes minus RD divided by RS1. So the ratio of those two resistances. But for that, your GM times RS1 has to be much higher than 1. All right, let's quickly look into the common drain configuration as well, which will be called the source follower. So in source follower configuration, it's common drain. So you'll effectively apply your input at the gate. You look at your output at the source, whereas the drain terminal will be the common terminal. You can also have a resistance over here, which is connected to the common terminal. Yeah, it all depends on where your input and output are. In this case, input at a gate, output at the source. That means it's a common drain configuration. Now, when you do the AC analysis, how the AC small signal model will look like is that, again, you have your input voltage here, that's your gate voltage. You have your VGS, that's the gate terminal, this is the source terminal. You have your RS1 connected at the source terminal. You have your GM times VGS flowing from drain to source. And you have this drain resistance connected here. Okay, let's just assume the output resistance of the MOSFET is tending towards infinity. You know the value of ID, the current that is flowing through this branch. The current that is flowing through this branch is equal to GM times VGS. So as in the previous scenario, you can find out your VGS to be equal to VG divided by 1 plus GM RS1. So it will be exactly same as this calculation, that VG is equal to, or VGS is equal to VG divided by 1 plus GM RS1. So that part of the calculation will be exactly the same. Now you know that your ID to be equal to GM times VGS. So GM times, because you know the value of VGS, you can just replace it over here. And you can write ID to be equal to GM divided by 1 plus GM RS1 times VG. Again, something that is exactly equal to the previous page or the previous scenario. Now, what would change? The change will be, or the modification from the previous circuit is just that the output is taken at the source. The current is exactly same as the previous common source configuration. Current is exactly same as the previous common source configuration. But the output is taken at a different point. So that's why the output voltage will be different. Previously, the output voltage was taken at drain. Now the output voltage will be taken at the source. So output voltage will be this GM times VGS, that's the output current, multiplied with RS1, that's the output resistance. So your output resistance is now RS1, the resistance across which you are taking the voltage. So now you put the values GM divided by 1 plus GM RS1 times RS1 times VGS. So what will be your voltage gain? Voltage gain will be output voltage divided by input voltage. And that will turn out to be GM times RS1, GM times RS1 divided by 1 plus GM RS1. So GM RS1 divided by 1 plus GM RS1. Now you can readily imagine if your GM RS1 is much higher than 1, let's say GM RS1 is equal to 99. So you have 99 in the numerator, and in the denominator you have 100. So your gain is almost equal to 100 over 100, or will be almost equal to 1, right? So that's why we were saying that it does not matter what would be the value of this RS, your gain in this case will be equal to almost equal to 1. And that's the use of your common drain configuration, which is used as a source follower with a gain of equal to 1. And that's the second stage provided in your homework number 5, that your first stage is just a common source with source regeneration as well as a bypass capacitance. But the second stage is a common drain or a source follower configuration. So the gain of it will be almost equal to 1, but you can calculate it to be whatever the value of GM2 times RS2 divided by 1 plus GM RS2. That will become your gain of the common drain or the source follower stage. Okay, so we'll stop here. Wednesday's lecture, instead of lecture, we have an exam at that time. I'll see you all on Friday again, and best of luck with your exam. Thanks.